Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi all, it's my pleasure to welcome Leonard Shulman. Leonard's a faculty at Caltech. He's also the director of the Caltech Center for Mathematics of Information. Leonard's a well-known researcher in theoretical computer science. His interests span almost all of the theory, from quantum computing to error correcting codes to approximation algorithms, and you name it, and game theory too. So he's going to talk about solvency games today. Leonard's been here for almost 2 months, and this is kind of his farewell talk, I guess. This is last week. We hope he keeps coming back. So over to Leonard.
Thanks, and just thanks for inviting me to visit Microsoft. And it's been great to visit. And there's 2 more days in which you can chase me to criticize errors in the talk. So I'm not out of here till Friday. I'm going to talk about work I did a few years ago with Noam Berger and Nevin Kapur, who were then both at Caltech, and Vijay Vazirani of Georgia Tech. But the first is a prelude. There's a saying in Hebrew that says, all roads lead to Rome. And I've since learned there's a new Hebrew saying. It says, all random walks lead to Redmond. So this talk is sort of about finance, and but also sort of about random walks, and of course the connection between. Well, it's not on my computer. Good. In The Wizard of Oz, there's someone standing behind a screen manipulating sudden things happening. That's what this feels like, because my computer is stable. Huh? I can just, right. Yes, right. As I was saying, this talk is sort of about finance and sort of about random walks, and the connection between these two fields or types of questions is long established, and this is from the 70s, I think, this book that sort of told you how to successfully make a lot of money on Wall Street by just trusting to Brownian motion or something. Strangely, we were sort of talking about this problem at the beginnings of it. We discovered that, as far as we could tell, and I would love to have my eyes open to literature we couldn't find, all this literature on how to make a lot of money by gambling speculatively, so all this kind of trying to, increase the rate of increase toward infinite wealth, doesn't seem to answer some really basic questions that we asked about just avoiding ruin. Now, investing for speculative gain can be, as I say, very alluring. For a while, some of you may remember when these predictions came out. There was the book was published called Dow 36,000, the new strategy for profiting from the coming rise in the stock market. Dow today is 11,000. There were other books. One said 100,000, one said 40,000. Apparently you could sell books just by picking a big number. But we learned our lessons, everybody, right? Well, some of us learned our lessons. This one was published in 2006. It seems like these books, are very good predictors of the future about 2 or 3 years after their publication. Again, we're kind of in this talk interested not in this highly speculative end of the question, but actually for us, it was more like, what's the investment strategy of a typical person, maybe middle class, or it doesn't have to be middle class, a person who actually isn't so interested in speculation. But really what you want to do is you have a standard of living. You want to, keep your house and food on the table and educate your kids. And you just want to invest to avoid catastrophic disruption. So that's a very different investment goal than Dow 36,000 or 100,000, or apparently they couldn't think of really big numbers. This actual same kind of question you might think should also come into the thinking of an insurance company. So an insurance company actually makes money by convincing you that they will stay solvent, and then they can sell you insurance premiums, right? And as a matter of fact, the prices in insurance policy companies themselves have ratings, and the premiums that they can charge depend upon those ratings. Those ratings we've discovered recently, can be very unreliable, but in any case, that's how that market works. The same thing actually happens in the banking sector. If you don't have, an insurance deposit, which is a sort of nice innovation in the United States, banks have the same issue of having to convince potential depositors that they in fact will stay solvent. And in the U.S. it's also true once you go above a certain amount. So there are these two investment goals. One is maximizing profit. The other is minimizing the probability of ruin. And they're related, but they're not the same. And this is actually the source of why we regulate these industries. If you've read the papers in the last year or so, maybe we don't really regulate these industries, but we think we do. So I want to start to be a little bit more specific about the type of, the phrasing of the question we'll ask. And again, I'll tell it through a little story. Suppose you're a wonderful card player. You can, you know the odds of whatever this card game is perfectly, and you can calculate on the fly. And you show up at a party, and it's just a bunch of amateurs. And there's two kinds of games you can play, and you unfortunately didn't arrive, you really want to clean them out. But the worst thing would be, the alcohol isn't very good. The worst thing would be to run out of your $50 stake and be stuck at this party. So there's two card tables that you could play at. And there are the following odds every time you play a round. Right? And you can choose what table to play at every time, depending on how much money you have in your pocket. But you arrive with $50. Table A looks like this. Table A, these are your personal odds, you, the expert. So the expert has positive bias, right? Positive drift. The expert can sort of, on average, make money. But here are his odds. He loses $3, 50%. And he has 50% chance of winning $4. So it's nice. He has a sort of expected gain of 50 cents every round of play. And table B looks a little bit different. It's the same game, but scaled up by a factor of 10, right? So 50% chance you'll lose $30 and 50% chance you'll win $40. And so the expected gain per hand is much more. It's $5. Okay? So, just psychologically, if you're interested in, if you're a speculator, you can see all the kind of type A jocks, heading toward table B. But if what you're really worried about is running out of money, you want to go to table A because it'll prolong by a factor of 10 the time to ruin if you do get ruined. So that was an easy comparison to make. We can all just... Oh, no, sorry. I actually, my last sentence was incorrect. But anyway, what I said was just wrong. But this is the comparison. Playing table B is the same as playing table A, but if you had arrived with only $5. That's the way to make the comparison. Sorry about that. There are more subtle comparisons you might have to make, though that one was particularly trivial. Table A, let's say, is just like you had before. You might lose or $3 or win $50, even stakes. But maybe it's like this. Maybe you either win or lose $3, but you have these sort of more nuanced probabilities, 0.42 versus 0.58. Again, there's positive drift, but this is one's maybe a little bit harder to kind of figure out which table you should play at. So the type of questions that we'll want to address is trying to resolve that kind of decision. If the best strategy is not to maximize the expected wealth, which would be sort of the or the expected drift, let's call it, which would be sort of the trivial thing to do, then what is it? You could say you should be doing the log, but that's not really the right thing either. So what should your best strategy be? And apart from the kind of, playing games version of this, sort of sociologically, we were curious at the time about this kind of question. You watch people living life and making very different kinds of investment decisions, depending on whether they're wealthy or poor. And you don't want to say that poor people are making bad decisions and that explains why they're poor. Well, sometimes that might be appropriate. But I think the question we're more interested in is the rationalization of this issue. That if you're rich, you can afford to take risks that, by and large, are profitable. But if you're poor, the probability of ruin prevents you from kind of taking these risks. So again, let's try and be a little more specific. An investment, or I'll start calling it an action, is going to be for us a finitely supported probability distribution on the integers. And just to show you tables A and C from our game a second ago, it means if you start at some origin, 0, which would be like your current wealth, there's 50% chance that you go to that wealth minus 3 and 50% chance that you go to that plus 4. And here similarly is table C. And in our setup, you have a choice between finitely many actions. So this is the framework. So at every value of the wealth, which will be some number W, you choose an action, you sample from the distribution. So an action is a probability distribution, and that's your new wealth. And this game continues until you are broke, and then the game is over, and you would like to play simply to minimize the probability of going broke. A strategy is a mapping from the positive integers to the space of actions. And it just says...
Wait, can I?
Yeah.
So you said that you want to minimize the probability of going broke, but you have to play a game each time.
But you have to play the game each time.
And you're probably going broke before when? By what
Ever.
time? Ever.
So...
Okay.
So you have
You're gonna play
to
forever.
have
Yeah. So in fact, I don't know, I say it on some slide, but let me say it now. In fact, we are going to assume that every one of these actions has positive drift. So, okay. So when you fix a strategy means which action you play at every value of wealth. We'll let P of W be this we'll call the ruin function, or given that you start with wealth W and you play this strategy, what's the probability that you ever go broke? And you'd like to minimize P of W. So here there are two very easy facts. For this audience, it's totally obvious. There exists a strategy for which P of W is strictly less than 1 for all positive W, if and only if there exists some investment in this collection that has positive drift. And also, you can play a Markovian strategy. I should just say, with respect to bullet 1 here, we're actually, again, I'm going to assume that actually all of them have positive drift for some technical reasons later on. And now coming back, well, one of the things, yeah.
Can I ask about that assumption? So, if you relax that assumption...
For this, right now, it wouldn't make any difference. I mean, sort of, but it actually changed. You might want to play something with negative drift, and there's some point in the results where that makes things complicated, and we don't actually know how to deal with it. Okay, so I'm going to describe this as sort of, this sort of additive. Everything will be phrased additively. But since we're not talking about expectation of your wealth or anything, it doesn't really matter whether we're working on an additive or logarithmic scale. In terms of the kind of, if we're talking about investment policies motivation, it actually makes more sense mentally to think of the multiplicative version, where this additive walk is happening on the logarithms, which just means, you invest in something and it goes up by 2% or down by 2%, sort of thing. And then going broke is not actually hitting $0 in that scenario, but hitting whatever your broker charges you for a minimum transaction fee. Okay, so everything translates perfectly. And And now back to the motivation about why do you have to play. The motivation why you have to play, I mean, again, if you're thinking about this not as a probabilist but as an economist, is there's no such thing as a risk-free investment. There's always inflation, and you sort of have to make some choices. So this is the weirdest part of the talk, the statement that, as far as I can tell, there's no literature on precisely this problem, because as you can see, it's an extremely simply stated problem. There's, of course, lots of work on Gambler's Ruin and probability, but that doesn't have to do with, but here we're talking about this sort of, not a single walk, but this strategy business. So let me just talk about what I know about the literature. And I warn you, pretty much what you see on the slide is my knowledge of finance. So just people, and if you've ever looked at how mutual fund managers get rated and things like this, there are these ratios people study. The Sharpe Ratio is maybe the best known of them, where you look basically at empirical data on something, a mutual fund or a single walk, but this strategy business. So let me just talk about what I know about the literature. And I warn you, pretty much what you see on the slide is my knowledge of finance. So just people, and if you've ever looked at how mutual fund managers get rated and things like this, there are these ratios people study. The Sharpe Ratio is maybe the best known of them, where you look basically at empirical data on something, a mutual fund or a stock or anything, and you look at the expected profit relative to some benchmark, relative to the S&P 500 or whatever your favorite benchmark is, or whatever is appropriate for that type of investment vehicle, and you divide by the standard deviation, again, just gathered empirically. And the higher this is, the better the kind of risk, reward-risk ratio. And the guideline people offer is sort of that, whatever your comfort level of risk, you should invest in something with a high Sharpe ratio. So these are some kind of heuristics that do nothing at all relevant immediately to our question. So I'll just leave it there. Now, in probability theory, people have definitely looked at sort of this kind of decision-making with respect to avoiding ruin, and I'm basically aware of these three papers. And the motivation is extremely similar. In fact, everything I've said up to now, except the post-2000 news in the market stuff, is very, could be taken equally from the introduction from some of these. But the model is different. They only study where there's only one investment available, and your decision is how much to invest. So you're trying to actually make a profit, and there isn't this business that I said a second ago about inflation. So in that sense, it's very, very different. Right? So there sort of is a safe choice, and you're trying to escape from zero. So in that sense, it's different. In operations research, our problem is a special case of some much more general model called Markov decision processes, where you have some space and you can make a decision. You're trying to minimize some penalty function or maximize some reward function. And it definitely belongs to that extremely general framework. It does not belong to the kind of really well understood special case. As far as I can tell, it does not belong to the extremely special, this special case that's very well understood called multi-arm bandits. So again, it doesn't seem to be treated by that literature. All right, so here's some questions we're going to try and answer and give at least partial answers for. First of all, is it true that in our does our model reflect kind of our understanding of reality that actually investment strategies do depend upon your current wealth? I mean, it certainly seems very likely, but the question is, does this model actually capture that phenomenon? Now, there's a related phenomenon that I think seems natural, which is that somehow it's really only this business of being poor that makes you choose something other than there's some optimal strategy that kind of, drives you off to infinity as fast as possible or something like that. And that you kind of, once you're once you're wealthy enough, you can just do that, and all the finer points of avoiding ruin happen in some finite region near zero. That seems like a reasonable suggestion. And if so, we would like to answer, which is that investment, which of your actions is not. And if it's not so, of course, we would like to know what the tail of this sequence looks like. And finally, we would like to know, can you actually compute how to behave? So these are the kind of things we're going to be interested in. So I'm going to spend maybe 2 slides or 3 slides on something that's purely probability theory, and for that reason, especially for this audience, I'll go through it very fast, which is just what's the theory of no actions, just random walk with drift. So, and partly just to set up my notation. I was thinking of taking out these slides, but I'll leave them in. So suppose that you have this one action A we're talking about. It's supported between the interval minus L to K. So you can lose at most L dollars, and you can gain at most K dollars. It's specified by sequence of probabilities indexed Q minus L through QK. These are probabilities. They sum to 1. The ruin P of W, remember, is the ruin function. P of W is in the kernel of the following map. So it's a you map the vector P of W to minus P of W plus the average of all the things you would go to, right? So this second term here is with probability QR. I go and I get the ruin probability of whichever random step I took. And the true ruin function should be harmonic with respect to this iteration. So it should be in the kernel of this linear mapping. And of course, you have to match the boundary conditions to the problem, which are that P of W is equal to 1 for W less than or equal to 0. So again, for this audience, I'm sure you're all happy with this, but for those if not, this is just like a Laplacian, except there's this asymmetry, and it's not just like a Laplacian. So the kernel of this map is the dimension K plus L. And it's spanned by these exponential eigenfunctions. So this is an eigenfunction. It's a function of W where these lambda sub I, there are K plus L roots. And they're the roots of this rational function. The rational function has a minus 1 for the fact that you left from position 0. And it has a plus Q sub R times x to the R at R ranging from minus L to K. Each of these functions is in the kernel for sort of obvious reasons, and they do span the kernel. And of course, we want to pick a particular element of the kernel, matching the boundary conditions. These are the boundary conditions that for W between 0 to minus L plus 1, the P of W is 1. There's something suspicious about this. It seems like you should need K plus L boundary conditions. And we only got L boundary conditions, so where are the missing conditions? They're not missing for 2 reasons. One is sort of abstract argument. Notice that the ruin function has to tend to 0. These are positive drift walks. So no matter what you do, if you start wealthy enough, you're probably not going to be ruined. So that means that the eigenvalues greater than 1, or the roots, I should say, greater than 1 can't actually show up with non-zero weight in this function. And then you have to prove this little theorem that says that this kind of function has exactly L roots in the open unit disk. And there's a nice little perturbation argument that shows that. There's another argument that's more constructive. Here I'll assume that the GCD of the positive Q sub k's is 1. Otherwise, you get some degeneracy. But everything's still true, but you get some degeneracy. And there's something called, I think it's called ladder random variables. Probably someone in the room can, probably many people in the room can. There's a nice way of looking at this, which is that for I between 1 and L, let alpha sub I be the probability that if you start with wealth W, then the first time you go below W, you hit W minus I. Okay? So these alpha sub i's are probabilities. They don't sum to 1 because, of course, you may not go below W, but they're positive, and they sum to at most 1. Then there's if you write things like this, you can get a nice kind of iteration on P of W that sort of only works forward. The hard part about writing the other equation is you depend on both larger and smaller values. Here you can just work your way up on the P of W's. You get this equation. The probability of ruin is the sum with these alpha sub i's of the probability of ruin given that you went down to W minus I. And this gives you a certain transfer matrix, which gives you the recurrence for P's. And if you look at the eigenvalues of this matrix, they are precisely the roots of that polynomial that lay in the open unit disk. This formulation sort of gets rid of the other eigenvalues. There's a unique positive eigenvalue, so this is going to be important for us later on. So just to point out, when I have these L roots in the open unit disk, there's exactly one of them on the positive real axis. So that's going to be important. And this is the Perron-Frobenius root of this matrix. Okay, so now I'm done with the kind of one action case. Now let's now talk about strategies and sketch out what the answers to those questions look like. So again, we're going to fix some finite collection of actions as script A. We need to define a partial order on strategies. So remember, strategies are mappings from the natural numbers into the actions. P sigma of W is going to be the probability of going broke at W in following sigma. So this is the ruin function of sigma. And there's a partial order on strategies which says sigma is less than or equal to pi. The smaller one is the good one here, right? If for every W, the ruin function of sigma W is less than or equal to the ruin function of, that should be a pi in that second superscript there. And we say that sigma is optimal if sigma is less than or equal to pi for all pi. That's an obvious definition. And the interesting thing is that it makes sense. In other words, we're going to show that there exist optimal strategies. So here's a theorem. Given any finite collection of actions, script A, there exists an optimal strategy. And furthermore, sigma is optimal if and only if it is locally optimal. Locally optimal means that sigma just has to have this inequality, just has to be less than strategies that differ from it in exactly one position. So they do the same thing for all values of wealth, except they disagree, and there's one wealth where they choose a different action. Okay, so this theorem says sort of two types of interesting things. One is it says there actually is a sort of a globally optimal strategy, and the other is that sufficient witness for that is that you're locally optimal. So I'm going to sketch out what this looks like. None of it should be, I think, it's all pretty straightforward. But so here's the sketch of how you do these things. We call a sequence of ruin probabilities, or a ruin function P. We'll say it's subharmonic with respect to some strategy sigma if, for all values of wealth, P of W is less than or equal to the expectation of P of W prime, where W prime is chosen according to this random walk, one step of the random walk starting from W. So that means where W prime is equal to W plus J, where you sample J from the distribution according to sigma. Okay? So that's the statement that that P is subharmonic with respect to sigma. And this is the expression where the Q's, these transition probabilities are those of sigma. And for this purpose, we want subharmonic to also include the condition that is true of all the functions we care about, which is that P tends to 0 in the limit W tending to infinity. And there are the obvious corresponding definitions for superharmonic and harmonic, where you just change this sign for superharmonic and put equality for harmonic. Here's the lemma we need. Fix a strategy sigma and any boundary conditions. So for example, it could be the boundary conditions of all ones, which is sort of what we care about overall, but for this purpose of the lemma, it's useful to know that this is true for any boundary conditions. And the statement goes, if V is subharmonic so V now is our function here. V is subharmonic with respect to sigma, and P is the unique harmonic solution corresponding to sigma. So for any strategy sigma, there's some Bruin function. That's the one that's harmonic. Then V of W is less than or equal to P of W for all W. I won't supply the proof. It's a lot of these, this like various other proofs in the paper are mimic what you know from normal sort of complex analysis about the maximum principle, and say, if there's a violation, there had to be a violation of the inequality. There had to be a violation of the inequality on the boundary of the region. So here the regions are sort of finite prefixes of the integers, but it's the same proof technique. So now we want to go back and prove that theorem about that there is an optimal and that locally optimal is sufficient witness for optimality. So we'll start with furthermore, the fact that if you're locally optimal, then that shows you're optimal. Let's let S be the Ruin probabilities or the Ruin function of some locally optimal function sigma. Let pi be any other strategy. By this lemma up here, S is actually subharmonic with respect to pi. So that means that S is less than or equal to the Ruin probabilities of pi, right? Because your local optimality it's enough to just look at this one location W. So S is less than or equal to the Ruin probabilities of pi. So that's sort of surprisingly short, but it works. So now we actually need to show that there is something that's locally optimal. First of all, we should note something really very simple, which is the space. I'm going to take a kind of a trivial topology, which is on the space of strategies, which is just I have the discrete topology on all actions in any position, and I take the product topology. Okay, it's a silly space, but it's nice to say things this way. That's compact, just by Tikhonov. And now, okay, that sounds like a stupid definition, but now I'm going to look at the following quantity. For a particular strategy, pi, I want to look at the sum of all of the Ruin probabilities. Okay? Now, because of the positive drifts of the strategies, I know that this sequence is dropping off exponentially. Okay, if I go to sufficiently high wealth, I'm probably not going to see the origin. Okay, so this always converges. And in fact, this, by really just using the same sentence I just said, this function of pi is actually continuous in the product topology. If I fix a long enough prefix, I can make this sum as small as I want. That's all it's saying. Ergo, some strategy sigma minimizes this sum, and then sigma is actually locally optimal, because if it differed from some other strategy pi at some location W, its Ruin probabilities would be some harmonic with respect to that other strategy pi. So there is an optimal strategy, and we can sort of have a short witness for it, if omega counts as a short witness. All right. So now we're going to come back. Remember, we had these other questions, like, is it true that then once you get far enough from the origin, you can just make your life simple and just always play this strategy that drifts the fastest or something like that? Right. So is that really true? So here's the theorem. Let's look at the leading root. So the Perron-Frobenius root. Right. So for each of these different actions, A, B, and C. Remember, there were some number of roots in the open unit disk. The number depends upon how much you could lose maximum with that particular action. So, but each one of them has one Perron-Frobenius root, meaning one root that's positive and between 0 and 1. So those were what I'm going to call these lambda 1s, lambda the action 1, lambda 1 of action A, lambda 1 of action B, and so forth. So the statement is, if lambda 1 of some action A is strictly less than lambda 1 of all the other actions, then yes. Then there's some tail in which you only play action A. So let's go back to an example I showed you at the beginning of the talk. This is where we had these two tables. One, you could lose $3 or win $4 with even odds. And then there's this other table where you would lose $30 or win $40 with even odds. And I can this again was the really easy example to look at. And in that example, lambda 1 happens to be 0.921 for A. And in table B, you just take the 10th root of that. So of course it's bigger, and therefore this is worse. So that was obvious by inspection even back then. Now we have a more complicated table, or a complicated alternative between A and C. To remind you, you could then lose $3 or win $3, but the odds were in favor of winning. So you can calculate lambda 1 of C happens to be 0.898, which is less than and therefore better than 0.921. So table C is in fact the rich man strategy in that game, even though table A has a faster drift toward infinity. And I didn't ask for a show of hands early in the talk about whether everybody thought the positive drift would be the rich man strategy if it existed, because I'm nice. Anyway, so it's an odd phenomenon. Once you think about these roots enough, you convince yourself that this is really the right intuition. But
this is true even for A and B. B has a bigger drift than A.
It's true even for A and B. So even that disproves this. Yes, that's absolutely right. But good point.
But because in A and C, your maximum loss somehow
is the same, right? Yeah. Okay. Yeah. Now there's also an algorithmic version of the theorem I just showed you, which is that under the same conditions, namely that there's some action whose leading root dominates, is less than the leading roots of all the others. If you pull out some of the conventional algorithms, actually I think any of the conventional algorithms used for Markov decision processes, you will actually converge to the optimal strategy. Actually, the only one I really know it for sure is value iteration. Value iteration is a simple thing. Well, actually, let me do these bullets in order. So the ingredients in showing that this to be correct is, first of all, we need actually some explicit bound on where the pure tail starts, because we actually want to say something about how long it takes you to compute this thing. So we can make these previous things quantitative and get some bound. And then at the tail, or at where you've cut off the tail, you need to sort of change the recurrence and actually put in those boundary conditions explicitly. The fact that you know it's just going to recur, so you can do that. And then you run value iteration. Value iteration is you start all the probabilities of ruin, or some, your current guess of them, to be 0. And then you update, making a greedy update. So you sort of said, well, if I'm going to choose at every W the action that would minimize my chance of ruin based upon my current estimate of what the chances of ruin are. And you just update it every time. And this updates in particular the ruin function. What you really update is the ruin function, not so much the strategy, if you will.
Leonard, I think you can give exactly this, in interpretation, just the ruin probability in J steps, and you're doing the iteration.
Good. That's right. That's right. That's right. That's right. Absolutely. So why does this actually converge? Actually, there's maybe a reason why it would converge from there, but this, so it didn't occur to me. But this, the way we anyway bound the convergence rate is by pretending that the updates were done with respect to the unknown optimal strategy, and which is just a linear update rule, and therefore you can just look at its spectrum and show it has operator norm less than 1. That operator norm is less than 1, but how much better than 1 it is depends on how finely this separation is spaced. On the other hand, I did a big setup job on this so-called rich man strategy, and the reason for the big setup job is it's false in general. So here's explicitly how you can falsify it. If you have two investments whose, again, they're prone Frobenius, these are two strategies, both of which lose at most $2. And if you cook them up so that the leading root is identical, so they fail the conditions of the previous theorem, but they have one more root that you care about, and those roots are different, then in fact the optimal strategy has an alternating tail eventually. And I'll just make a very quick sketch of a slightly weaker claim that it's just not a pure tail, which is shocking enough. was to me when we did this. I'm not saying you need to be. So suppose you were pure and you were playing A from capital W and on, and we'll let S be the Ruin function of sigma, of this supposedly optimal sigma. Then you can write down, once you get a little bit past W, you can write down exactly what the Ruin function looks like. It's a combination of these two exponentials, where here lambda is this common Perron-Frobenius root, and lambda 2 is the other root of A. So it's just this sum of two exponentials. And I want to just point out now that lambda 2 of A and lambda 2 of B are negative. Remember that? I kind of emphasized before that there's only one positive root. And since this was a real polynomial and you only got one other root, it's negative. Then if you look at the value of playing B at W plus 3 minus this Ruin function at W plus 3, you get an expression which, yeah, so this is some, oh, sorry, there's a mistake in this expression. There's a QB. QB was the rational function value. I was mistaken. The main thing to pay attention to is this term. Sorry for the error in the second term there, where you have the lambda 2 of A to the power W plus 3 times some constant. We don't care what that constant is. But if you look at W plus 4, you have the same kind of expression with a W plus 4, remembering that lambda 2 of A is negative. These guys have opposite sign. And this was this quantity, this difference that we're looking at here is the kind of sub or super harmonicity. So one of these is not as good as it could be, and you can make an improvement. And a simple corollary of that is that even when there is a pure tail, it might start arbitrarily far out. It's not bounded by K and L. It's actually bounded by that separation of the roots. Yeah?
So can you, probably the answer is yes, a similar example. Can you show that the optimal strategy maybe in the tail is not just to pick the choice which would be best if you picked that as a pure strategy for all?
Can I, no, what?
So given a wealth, you can say what would be your probability of ruin if you always picked option I.
Yeah, right.
Option I.
Yeah.
And that gives you a number. So presumably it's not true that the optimal strategy for a large enough W is to just pick the option which is...
I'm sorry, I'm not sure why I'm not understanding this, but...
So for each investment option,
yeah.
I, and for each W,
yeah.
there is a ruin probability.
If you would just...
You just always play that no matter...
The ruin function of this pure... Yeah.
Right, so...
Oh, I see. You're just saying, could I...
I mean, it can't be, but you're right. The optimal strategy is not just to pick the one that's best if you play that.
There's no reason for it to be that. I mean, no, I don't have...
But that probability is basically the lambda to the power W, so it's not...
But the setup conditions before the pure tail kicks in matter too. I mean, for example, there might have been a third strategy that's not even playing a role in the tail.
Right, but matter for both of these
shifts these probabilities.
So,
but the question you're asking is sensitive to, well, it's sensitive to what these...
Yeah, I mean, so I imagine similar examples could...
Okay, so I don't know that wouldn't be, but I would be really surprised if it I don't know. So there's a bunch of open problems. I think our results don't, really go all that far. We don't, for example, know if the tail of the optimal strategy has to be periodic. We don't have an algorithm for the case where that rich man strategy theorem fails. Probably you want to answer the first part first, the first question first, because if you at least knew they were periodic, it would be at least clear that there's a short witness for what happens in the tail, and you could just write that down. But if it turns out that the answer to the first question is no, then the second one becomes a much more interesting question because of some more elaborate characterization. Finally, there's really no reason except technical reasons to stick with the case of integer increments. Really, I mean, last time I checked my broker statement, I wasn't losing or making exactly an integer number of percentages on each of my investments. It just doesn't doesn't really make sense, except it's a lot easier to do. So I think that would be, if you're sort of something to get a handle on.
But existence of an optimal strategy might somehow use some kind of compactness or something, but not necessarily.
Yeah. Everything becomes an operator. I mean, it just becomes technically one. I don't.
Right, but you can imagine a situation where there's no optimal strategy simply because there's always something a little bit better than
Yeah.
you do.
Right. No.
So if you have only finitely many actions,
Yes, but you might, like you said, extend it to the case of knowledge.
if you have finitely
No, it's still finitely many actions. Still finitely many actions, but the if you will, the group that these guys generate is dense. I mean, so then I sort of don't know what to.
still something to prove it.
Okay, so as Nikhil said, I'm out of here soon. I've had a wonderful time. Thanks for having me here. I hope I see you again soon.
Thanks for all the fish. I thought you'd show, I love sushi instead of
I went to I Love Sushi. It was wonderful, but taking my family to the aquarium was actually even more wonderful.